Good afternoon. How's everybody doing? Awake? Cool. My name is Kavya, and I'm here today to talk to you about analyzing real-world systems using performance modeling, which is theory. Now, why in the world might we want to do this? Well, ideally, we want to give our users a good user experience, so we care about things like response time. And ideally, we want to do so without breaking the bank. So we care about things like server utilization, capacity planning. And so as systems designers and builders, as performance engineers, we spend many a night trying to answer questions like these. How much load can my server handle? Do we need more servers? Are we already over-provisioned? Does this sound familiar? How many people here are intimately familiar with trying to answer questions like these? All right, just about everybody, right? So you know there are a few standard approaches to go about trying to answer these questions. The first is what I like to call the hashtag YOLO method, where you try something and hope it works. We've all been here. The second method is load simulation, where you gradually apply a load to your production system with the goal of stressing the system to try and determine the actual performance characteristics and bottlenecks of your system. Now, I'm a big believer of load simulations, so we'll come back to this briefly throughout the talk. But the focus of today's talk is going to be the third approach, namely performance modeling. Now, performance modeling speaks to this idea of taking your real-world system, representing it by a theoretical model, analyzing the model to get results, and translating those results back to your actual system. Now, the crucial thing to remember about performance modeling is that modeling, by definition, makes assumptions, right? In the case of queuing theory and queuing theory models, which is what we'll be looking at today, it makes assumptions about the arrival rate of your requests. It makes assumptions about what order requests are processed in, the service time distribution of your requests. And so, in order to use these models, in order to use the results of these models, your system needs to satisfy the underlying assumptions. If they don't, you might still be able to leverage the model, but you can't apply it blindly. All right, so we'll be looking at performance modeling today to answer questions about our system's performance and its capacity needs. Specifically, this is how the talk will be structured. I will first talk about analyzing a single server system. We'll then talk about analyzing a cluster of servers. And then finally, we'll take a step back and see what we can take away. All right, then. Let's get started. So a single server system, we are going to assume, so say, for example, our model is a simple web server. It receives requests from a client. It processes them pretty standard. Now, the questions we typically have about such a system are, what's the maximum throughput the server can support without falling over? That is, given we have an SLA, a response time or latency threshold that we don't want to cross, what's the maximum request per second we can serve? So in this graph, for example, at 4,000, 4,500 requests per second, we're still nice, our response time is still nice and low below the threshold. Our question is, what about, can we serve 5,000 requests per second? What about 7,000? What about 10,000? And the second question we might care about in such a system is, well, how can we improve our mean response time to give our users a better experience? So we're going to use performance modeling. Specifically, we're going to model this server as a queuing system. The way this works is requests come in at some arrival rate. If the server is busy, the request is immediately processed. If the server is free, if the server is busy processing other requests, the requests queue. Now, the time they spend in the queue is called the queuing delay or the waiting time. We'll be using the term queuing delay today. Finally, when the server is free, it picks off a request from the queue and processes it. The time the server takes to do this is the service time. And finally, a response is sent. Now, we're going to make some simplifying assumptions about our system. The first is that requests are independent and random. That is to say, the requests, they're not correlated with each other. They're not correlated with the response time of the system. No, they're independent and random. It's a random variable. The second assumption is that requests are processed one at a time and in first out order. So you can imagine this is a single core, single threaded server. And finally, we're going to assume that the service time, the time it actually takes to process each request, is constant. What this means is we're assuming that requests are the same size. They take the same time to be processed. And we're also assuming there's no downstream saturation. The database, the network, nothing gets saturated. This allows us to treat the service time as a constant. All right, so our first question, what's the maximum throughput of this server? Well, using our queuing theory model, let's just reason about it intuitively. Say we crank up the arrival rate at our server. What happens? Well, our server's utilization, its busyness, increases. Now, there's nothing revolutionary about this. It's like your boss shows up and gives you more tasks to do. You're going to spend a larger fraction of your time being busy. Same idea. But our question is, what we care about, is how does the utilization increase with arrival rate? And queuing theory has a formula called the Utilization Law, which tells us that the utilization is equal to the arrival rate of requests times the service time. If you think about it for a second, it makes sense. And since we're assuming service time is constant, what this means is that the utilization arrival rate graph is linear. It's a line. All right, so now our server's gotten busier. What does this mean? Well, it means that the probability that an incoming request comes in and finds the server busy and therefore has to queue, that probability goes up. So the probability of requests needing to queue goes up, which means that the mean queue length, the average queue length increases, which in turn means that the average queuing delay increases. Does that make sense? Yeah. Cool. So again, our question is, well, how does it increase? What is the relation between utilization and queuing delay? And for this, queuing theory gives us another formula called the PK formula. Now, the PK formula has a full name that is somewhat hard to pronounce. I think it's the Polak-Zek-Kinshine formula, but we're going to call it the PK formula. And the PK formula tells us that the mean queuing delay has a dependency, that dependency on the utilization of the server. And there are two other terms that we'll come back to later, but those two terms depend on the distribution of service times. Now, the reason we're going to come back to this later is because we assumed that service time is constant, so we don't need to worry about those two terms right now. So we can say that the mean queuing delay is directly proportional to that term, the server's utilization, U over 1 minus U. What does that look like in practice? Does anybody know what that function looks like? It looks like a hockey stick. What this graph tells us is as utilization increases, the queuing delay is going to increase in that manner, and that makes sense, right? When U is large, the denominator approaches 0, which means the entire fraction approaches infinity. Now, because the response time is the queuing delay plus the service time is constant in our model, response time is directly proportional to queuing delay. So what this means is that the response time utilization graph is the infamous hockey stick that we're all probably familiar with. All right, so back to our question. What's the maximum throughput of the server? Well, what happens when we increase the arrival rate? We know that initially, in the low utilization regime, response time is going to remain approximately the same. But as soon as we're in the high utilization regime, the response time is going to start to hockey stick. So when we're in the high utilization regime, increasing the arrival rate is not going to improve our system's throughput. At that point, the system, your server is busy. It's as busy as it can be. It can't do any more work. So at that point, increasing arrival rate is simply going to increase the response time of your requests. So what's the maximum throughput anywhere? Well, the maximum throughput is right around 5,500 requests per second. So that's around when our response time threshold is crossed, right? Because response time hockey sticks. It doesn't stay constant. Cool. So this answers our first question. Moving on to our second question, how can we improve the mean response time? Well, we just saw that response time depended on queuing delay, right? And we just saw that response time started to get bad when queuing delay increased. So here's an idea. What if we just prevent the queue from getting too long? That should take care of it, right? That's, in fact, an excellent idea and a pretty common way to address this problem. A few common strategies that you're probably aware of are you set a max queue length, and if incoming requests find the queue full, those requests are dropped. Another common strategy is client-side concurrency control. So on the client, you time how long your request to the server takes, and if the server's starting to take too long, it means the server's overloaded, your requests are queuing, so you back off. You stop trying. Read this as a form of circuit breaking. But there are a couple of novel or uncommon approaches that I'd like to talk about. The first is this idea of controlled delay. This is an algorithm that Facebook implements in their Thrift, in their RPC framework. And the key insight of controlled delay is that queues are normally empty. You still want to have a queue for reliability to absorb burstiness in your traffic. But even so, your queue is normally empty. So if your queue has not been emptied for a long time, so your queue has not been emptied in the recent past, it means your server is overloaded, and so you start timing out requests sooner than you would otherwise. So this is what the algorithm looks like. It basically checks to see when the queue was last emptied. If it was greater than some threshold time ago, you enqueue the request, but you set a short timeout, right? So that's CODEL. A second uncommon and interesting approach is you process requests in LIFO order, in last in, first out order. Now, Facebook implements this as well in their PHP runtime, and they use adaptive LIFO. So they start off, their queues start off as first in, first out queues, and they switch to last in, first out when they notice that the server is getting overloaded. But Dropbox recently released an article talking about their reverse proxy Band-Aid, and Band-Aid always processes requests in last in, first out order. Now, why do they do this? Well, the insight here is that when the server is not overloaded, it doesn't really matter what order you process requests in. However, when the server is overloaded, it makes sense to process newest requests first, because your oldest requests have been sitting in the queue for the longest amount of time, so they're likely to time out. So there's no point in wasting resources on them. Okay. So so far we've seen methods to control the queue length. These are somewhat reactive methods, right? They intercept the queue length. Can we be more proactive about it? Well, let's go back to the PK formula, because that tells us a few things we can do organically to prevent the problem. So remember the PK formula. Now we're looking at those last two terms of the PK formula. It tells us that queuing delay has a linear dependency on the average service time. What does that mean? Well, we can spend some time decreasing service time. We can optimize our application code, our request handling code. And that, you see that that's the graph, on the green graph. You see that it hockey sticks much later than the original graph, which is the blue line. The PK formula also tells us that queuing delay has a quadratic dependency on the service time variability, right? Which means that if your requests, the time taken to process each request, if there's a lot of variance in that, that's bad, because that causes more queuing. And so we can try and decrease the variance, for example, by batching requests in order to make sure that they all take approximately the same amount of time. And this is what the graph looks like. The blue line here corresponds to the blue distribution where you have many service times. And the green graph here, which hockey sticks much later, shows us that if your tasks all have the same size, then your queuing delay is less. Cool? All right. So at this point, we've answered both our questions about throughput and improving response time for this single server question. So here's a question. Do all single server systems look like a web server? Nope. Here's another single server system. In this case, imagine that you are an IoT company. So you have a number of sensors out in the field. These sensors, say they're temperature sensors. So they measure temperature, and they periodically upload data to your backend server, which is sitting in the cloud. And your backend server processes data from these sensors. Now, the actual code on the sensors might look like this. The sensor synchronously, so it sends a blocking request to the backend with some data. It says, upload this batch of data. It waits for the server to ack it, and then it goes to sleep. This is to preserve power on the devices. And then, say 5 seconds later or some z seconds later, it wakes up and it sends the new data to the server. So the question is, can we use the model we used to analyze the web server? Can we use that model to analyze this system? Nuh-uh. This is a very different system in two important ways. The first is that requests are synchronized. Each client's request is synchronized. What do we mean by this? Remember, a sensor sends data. It waits for the response, and then it sends the next request, right? So there's almost a feedback loop. And secondly, we're assuming that there's a fixed number of clients. So the queuing theory model for such a system looks like this, right? This model, we need a model that captures those two properties. So there's that feedback loop between the response and the request side, and we have a fixed number of clients. Why do these differences matter? Well, these differences mean two important things. The first is that throughput depends on the response time, right? There's a negative feedback loop built into the system. Because if your clients send some number of requests, and those requests, your response time's taking longer and longer, those clients will be waiting for the responses before they send out another request, right? So they naturally will not send out any more requests, so your throughput decreases as your response time goes up. It's an inverse relation. And the second important way in which this system is different is, in this case, the queue length, the maximum queue length, is bounded. We have a fixed number of clients, n, and each client can have at most one outstanding request to the server, which means your maximum queue length can be at most n. Make sense? Cool. So such a system is called a closed system in the theory. And as you can see, it's super different than the open system that we previously saw. OK, so our question, again, is what does response time versus load look like for this system? First things first, the assumptions we need to make. The first is we're going to assume that the sleep time is constant. So every device sleeps for a fixed z seconds. As before, we're going to assume that requests are processed one at a time and in first in, first out order, and the actual processing, the actual service time, is constant as well. OK, so let's see. In this case, to increase the load on the system, we have to increase the number of clients, right? Each client has one outstanding request, so if you increase the number of clients, you have more requests. Okay, so as we increase the number of clients, like we saw before, throughput originally increases until utilization is high, until the server is as busy as it can get. And beyond that point, increasing the number of clients simply means your requests are starting to queue. So queuing increases, right? Which is why throughput looks like that. In the low utilization regime, it grows, and then it flatlines. And what we're interested in is what happens to response time in the high utilization regime, in this case. To answer that question, again, we turn to the theory, which tells us to use Little's law. Now, before we talk about Little's law, I'd like to clarify how this model works so we're all on the same page about it. Now, the system in this case is the entire loop, okay? So we can take a request as being in 3 states in the system. It can be in the sleeping state on the devices. It can be waiting in the server's queue, or it might be being processed, so in the server itself. And so the total number of requests in the system includes the request across all 3 states. So it includes the requests on the sensors, on the devices, and the requests being processed on the server or in the server queue. So Little's law gives us a formula for the total number of requests. And Little's law tells us that this number is equal to the throughput times the round-trip time of a request, the total time a request spends in the system, which is the sleep time plus the response time. Okay, so since we're in the high utilization regime, we set throughput as constant. We're also assuming that the sleep time is constant, which means this formula simply becomes the number of requests in the system. This has to be equal to n, like we said before, because we have n clients. And this is simply equal to a constant times the response time. Does this make sense? OK, so what this is telling us is that the response time, in this case, it only grows linearly with n. It doesn't grow unbounded. So going back to our question, when we're in the low utilization regime, response time stays about the same. But when we're in the high utilization regime, it grows linearly with n. Putting those 2 pieces together, this is what our response time graph looks like for a closed system. It's initially it stays pretty flat. You can't see that portion very well in this picture, but then it becomes a line. And this is way different than the corresponding graph for an open system, which looked like this. In the high utilization regime, if we allowed the queue to grow unbounded, response time would tend to infinity. OK, so at this point, we've talked about open systems and closed systems, and we've talked about how they're different. What this implies is that we probably shouldn't model an open system using a closed system model and vice versa, right? There's only one problem. And the problem is, does the closed system remind you of anything you might use? Load simulators. Most standard load simulators typically mimic closed systems, right? You have a number of virtual clients, virtual users. Each client sends a request to your production system. It waits for a response. There might be sleep built in, and then it repeats. This is a closed system. But your actual production system with real users might not be a closed system, right? It might be an open system, or there is research that shows that most real systems lie somewhere in between the spectrum between closed and open systems. They're called partly open systems. The big takeaway here is that if you're using a closed system type simulator, you need to be aware and wary of the results you get. Specifically, your load simulation might predict lower response times than you'd actually see in your production system. There are other differences. Closed systems tend to show a better tolerance to variability in request size than open systems, and scheduling algorithms produce different results for what's good in closed systems versus open systems. Are there workarounds? Is this something we can do? The answer is yes, there is. The workarounds are somewhat involved, so we won't go into the details right now, but if you're curious, ask me later. I do encourage checking out these two neat papers on the topic. There's open versus closed and how to emulate web traffic. The links are on the slides, which answer the question in detail. OK, so that's single server systems. Now let's move on to a cluster of many servers, because really, our production systems look like this. What are questions we might be interested in for these systems? Well, questions of capacity planning. How many servers do we need? And questions of scalability. How can we improve how the system scales? Right? How can we get higher throughput from by increasing the number of servers? OK, so let's start with the first question. How many servers do we need? Well, we know the maximum throughput a single server can support, right? That's what we just looked at. If we have a cluster of n servers, is the throughput of the cluster simply n times the throughput of the single server? I wish. Systems don't scale linearly, right? So this is not the case. And systems don't scale linearly, typically, for two reasons. The first is contention, right? Where the idea is there's some fraction of your workload that cannot be parallelized. There's a serial fraction to your workload. And for that fraction, when you increase the number of servers, you're increasing the contention penalty, right? This is also captured in Untitled Law. A classic example is serialization or contention for shared resources. For example, database contention, lock contention. An example that I like to use is if you have a scatter-gather type workload where there's a scatter phase and then you have the gathering, you can, by increasing the number of servers that are performing the scatter phase, you can increase parallelization to some degree, but then at the gather phase, contention is going to increase, right? So there's a contention penalty there. And this contention penalty can be expressed as alpha times n, a constant times n. And all this captures is that the contention penalty increases linearly with the number of servers, which is what you'd expect. The second reason why systems don't scale linearly is crosstalk penalty or coordination penalty, consistency penalty. The idea here is if your systems need to coordinate, typically they need to coordinate to synchronize mutable state. But if there's coordination in your system, then the worst case penalty is when each server has to talk to every other server, has to coordinate with every other server. So this penalty scales a constant times n squared, right? So the penalty here is quadratic with the number of servers. OK, so we know our cluster might have to pay these two penalties. Again, our question is, how does this affect the throughput? And the answer to this is given to us by the universal scalability law. Now, don't let the formula scare you. It makes intuitive sense if we work through it. The idea here is if there is no contention in our system, and if there is no coordination, and we're not paying those penalties, then we'd get the much sought after linear scaling, right, which is the line over there. Now, if we have only contention and not crosstalk, then this is what the graph looks like. You see throughput, this concurrency on the x-axis and throughput on the y-axis. So you see throughput initially increase and then somewhat flatline. And if there's both contention and crosstalk in our system, then bad luck, because the theory says you start to actually see retrograde scalability, where throughput actually starts to decrease. There are examples of this online in Baron Schwartz's blogs and Neil Gunther's blog posts. I personally have not seen this. All right, so that's universal scalability. And that helps us answer the question, what is the throughput of my cluster? Now let's ask our second question. How can we improve how the system scales? Well, the universal scalability law tells us where to look. It tells us to look for sources of contention and crosstalk and to eliminate or reduce those, right? Because that is what is preventing our system from scaling linearly. Some real-life examples, real-world examples of doing this. Facebook has a caching service called Tau, and they use smarter data partitioning to help their cluster scale better. So they had an old partitioning algorithm which made it so that a greater fraction of the popular data ended up on just a few servers. And as a result, there was contention for those caching servers. What they ended up doing is use a smarter partitioning algorithm, so the popular partitions were more balanced across servers, and that helped their throughput get higher, their caching service throughput cluster get higher throughput. Another example is by using smarter aggregation. Another example of this is in Facebook's Scuba time series data store. This is sort of a scatter-gather system in that the data is partitioned across a number of leaf nodes, and you have an aggregator node that when you make a query for time series data, it performs aggregation across the data nodes. So rather than having a flat hierarchy where you have one aggregation node and you just scale up the data nodes to accommodate more data, they structure Scuba as an aggregation tree, so you have several levels of aggregation. And the thinking here is you can parallelize the aggregation step better. And finally, other things you can do is you can use better load balancing strategies, again, so that your loads, there's less contention for a few servers. Best of two random choices is what is used in most systems at companies like Facebook and Google. You can use fine-grained locking to reduce contention. You can use MVCC. Most databases today support MVCC, and so on and so forth. All right, so, all right. It is now time to take a step back and consider what we can take away for our systems, right? Today we looked at analyzing single server systems, open versus closed. We looked at analyzing a cluster of servers. But we've barely scratched the surface of performance modeling, right? However, we do know enough to try and take this and attempt to apply it to our systems, which raises the big question, which is, where does performance modeling fit in our toolkit? In my opinion, performance modeling is the most useful and the most powerful when used in conjunction with more empirical methods of performance analysis like load simulation and performance experiments, right? Because performance modeling makes assumptions that might be difficult to validate in practice. For example, the queuing theory models we looked at require you to know your service time distribution, or at least its mean and variance. And in practice, this is difficult to get, right? Because even before the request hits your application, you can instrument that. But even before it hits your application, it's going to spend time in TCP queues and what have you. But performance modeling, it does give us a rigorous framework to do a few things. The first is it gives us a framework to determine what experiments to run, right? You run the experiments that you need to get the data in order to fit the USL, the Universal Scalability Law curve, or your response time graphs. It gives you a framework in which you can to interpret and evaluate the results of your experiments, right? For example, you know that load simulations, the results you got, your load simulation predicted better results than your actual production system. Now you know why, right? Or here's another example I like to use. So you run a load simulation with N clients where you increase the number of virtual users, and you get a response time graph like the one on the right. Well, you know that that graph is the wrong shape. Response time doesn't behave like that. Response time behaves like one of these graphs on the left, right? And we know that from performance modeling, from the theory. And finally, it gives us a framework to help us determine and decide what improvements would give us the biggest wins, right? Where we need to focus our efforts to help our system's performance and scalability. All right. And with that, it's time to say goodbye. Thank you all.